All right, so let's just talk about this first one. We'll stop and go, and see what memory serves. Here you go. Here's your center of the circle, and here's one radius, and here's a second radius. And the clock is divided into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 even sections. So that 360 divided by the 12 means that each section is 30 degrees. So when I talk about a 5 o'clock angle, that's going to be 1, 2, 3, 4, 5 times 30, which gives me a central angle of 150 degrees. Thumbs up if you got that far. Awesome. If my central angle is 150 degrees, then so is the arc defined by those radii. So if you want to name it arc AB, I know that the measure of arc AB is going to be equal to 150 degrees. So however you want to name it, that's fine, but let's talk about some of the notation. We talked about the M is going to be your measure, so think of it as the measure of an angle. That's where you've seen that M before. This arc means that it's around the outside of a circle. It's similar to like what you do for a segment, right? But it's little eyebrow up there, and then you measure it in degrees. How we doing? Good? Now, I have no idea how big the clock is. I've got a clock there, I've got a clock there. My daughter's, did I tell you this is hilarious? See this analog clock that she put on the front of my phone? Like, she did it for me because I look at, like, I need an analog clock because I glance at it. And if you said to me what time it is, I'd have to look back. But just by the position of the hands, I know where I am in my day. Does that make sense? She's the exact opposite. So I have it on my phone because it's a quick, no-read glance for me to know what time it is. I know where I am in my day. I know where I am in my lesson. I know where I am for where I need to be. She's the opposite. She doesn't know how to read those clocks. Do you? She's 23, y'all. And she was raised in a normal household, right? And she went to school here. She doesn't know how to read those clocks because she's always had a digital on her phone. So she decided as a productive member of society and a well-functioning young adult, she needed to put her on her phone and learn it. So she tests herself all the time whether or not she can tell what time it is by reading it. That through always cracks me up. I can quiz her. She can't read cursive handwriting either. How about you? No? Do you struggle with my handwriting because I write in cursive? No? A yes here. Kyle says yes, I do. So reading that clock, depending on what size your clock is, the distance from A to B around the circle is different. So it's not until I have a radius measure can I go ahead and tell you how far it is on this clock. Once they tell me I have a radius of 8 inches, if I wanted to know how far around the outside of the clock does the big hand travel to meet the little hand. Now, just one disclaimer. As the big hand moves, so does the little hand. So a really complicated calculus problem is when do they meet up? Because in most clocks, this little hand is moving. As the big hand is moving, we're going to pretend it's not. We're not going to get that complicated. But how far around the outside of the clock does the big hand travel to meet the little hand? So I know that if I have 150 out of the total 360 degrees, that is my part to whole story. That is what fraction of the circumference I need. So you are of two minds. There are two options for how you solve this. You decide which one you are. Are you a proportion person where this part to this whole is equal to this part here that I'm solving for compared to 2 pi r? That's if I solve it by doing a proportion. if I solve it by writing equation, that distance I'm looking for, this x value, is equal to this fraction of this whole. And this whole is my circumference. So this here is my circumference. This here is my circumference. And remember, your circumference is 2 pi r or pi d. Both of those equations will give that to you. Would you please talk to your group mates and share which one of these makes most sense to you? Are you an equation thinker? Are you a proportion thinker? And then I want you to agree on the solution. Go. All right. So notice the calculator keystrokes are the same, and I'll show you my calculator so you can see what it is I typed in, because I typically do this work in two parts. I did 150 times 2 pi times 8. 150 times 2 times pi times 8. If you want to call that 16 because that's easier, go ahead. Once I get that value, when I solve for x, I need to divide everything by 360. That's fine. Notice the same exact keystrokes are true over here. I did multiplying fractions are no problem, top times top. 150 times 2 times 5 times my r, which is 8. And then that whole thing times 36. Or divide by 360. If you are interested in shortening your work, you can always simplify this fraction. And that makes those numbers a little bit easier. If you did 15 divided by 36, that's the part of the circle that I'm interested in. So it's that times, see if it tells me, there we go. That times 2 times pi times, and my radius is 8, and you should get the same exact answer. Multiplication is commutative, so whatever order you do it in, nobody cares. Whether you do 2 times pi first, or 2 times your radius first, or dividing this fraction and then multiplying that piece of the whole, you just got to do whatever makes sense inside your head. All right, number 3 is a completely unrelated problem in circle B. So go ahead and draw a sketch of circle B. In circle B, there it is. The length of arc ST from S to T is 3 pi. And the measure of arc ST is going to be 120 degrees. What is a radius? On your mark, get set, think, go, talk. All right, do we agree? So I set up by proportion. Here's my piece to my hole, 120 out of 360 degrees. And I went to cross off my zeros to cancel that out and simplify it, but then I realized, oh wait, isn't 12/36 1/3? So anytime I can simplify my fractions, it's easier numbers. I like that better. When I look over here, this piece to this whole, if the length of arc ST is 3 pi, that's the part of my whole. My whole is 2 pi r. I'm going to cancel those pi's out. Everybody okay with that math? So that leaves me 3 over 2r is equal to 1/3. So then I have 2 times r is equal to 3 times 3. I did cross products, which means r is equal to 9/2. How we doing? And I guess I should call that inches. Okay? So we're going to try to do everything we can to spin these around and make you solve for different pieces of this conversation. This is your measure of your central angle and your arc compared to your whole, 360 degrees. This is the length, the linear distance of this arc, and this is the circumference, the distance around the whole circle. They both fit that part to whole story. Do me a favor and write down something in the top part of this here to help you remember something to make it easier for you to solve these problems. What do you need to make sure you remember to solve these? Write yourself a note. Dear Layla, make sure you remember part to whole, degrees, measure versus length. Measures in degrees, length is in inches or centimeters. Write a proportion. Radius is half the diameter. Circumference is the distance around the circle. Pi d is the same as 2 pi r. Whatever note you need to write yourself, and then share your note with your group. Go. So on the back, what is the difference between the front and the back? Conceptually. What is the difference between the front and the back? What are we talking about? What are we solving for? What are we looking for? Go ahead. Yeah. So if you think about that difference between perimeter and area, perimeter is the distance around. If I were to draw or to put a string around the entire perimeter of the room, it's a linear length. That distance plus that distance plus this distance plus this distance. That's how much string I would need. If I was painting the floor or carpeting or covering my entire floor, that's area. So the difference between when we're talking about that arc length versus sector area, that's the difference between tracing something around and filling it in. So you know how when you go to color something in, my sister was always a really good colorer. So every time she went to color, she would always trace her shape first, and then she would color it in. Anybody do that? Anybody that kind of colorer? Her pictures were always beautiful. Mine were a mess. I was not a coloring inside the lines kind of kid. So once you think about the difference between tracing around the outside of the circle, and then when we're finding area of the sectors, we're coloring it in. All right, so here's the thing. We can find the area of these two sectors separately and add them together. Would you divide your group mates and your new partners? And remember, partners go this way. So Gabby and Lila are going to, the partner on the door side of the room, you're going to find this sector area. The partnership on the window side of the room, you're going to find this side or this sector area. And then you're going to go ahead and add them together for the whole. On your market set, go. Big guy. Okay, and you can check. All right, so come back. Let's talk about this. Come back. All right, so there's a couple different ways you can do this. If you get your mind straight, you're like, this is the process of how I solve it, then I'm going to do it, that's fine. If you want to do your part to whole and set up your proportion and do your math, that's fine. But you can also just find the area and take a quarter of it. Because 90 out of 360 degrees is a quarter, right? So you should have ended up with 19, my first group, 19.63 square inches. And I heard somebody go, I don't understand what they mean by in terms of pi and exact answers. A lot of times they leave the answers in pi so that you don't have to deal with an irrational number and rounding. Same with simplifying radicals. Once we go to simplify an irrational number, We lose our true value. So it's compromised. Can't do that. All right, when we talk about my purple area, 40 out of 360 degrees, that's going to be 1/9. So if you want to, you can just take 1/9 of the area. Now, what's interesting, if I have a 1/4 and a 1/9, I can look at these two things and see if that makes sense to whether I better had gotten a smaller answer for this one than that, just proportionally. This one's going to be a little less than half. 45 degrees would be half of this area. And see how it's a little less than half? So I'm in good shape. So just by looking at my answers and estimating, yeah, 8 is a little less than half of 19. Looks like my calculations are good. When we add them together, my 25/9 pi and my 6.25 pi, that's not going to work real well. So I just go ahead and I round to the nearest hundredth. So once you find the area of that individual sector, you can add them together, no problem. All right, we talked about what a segment was when we were together and doing our notes. And what I want to do is do one with you so that you can see it for sure. Because our first step in solving the segment is to go ahead and get the area of our sector. So when we find the area of our sector, that's 75 out of 360 degrees that I care about. And I'm going to find the area of this whole triangular wedge. And that's going to be equal to what I'm looking for times pi times my radius squared. So then my x is going to be equal to 75 times 4 times pi. And that's all going to be divided by 360. Popping over to my calculator, no problem. 75 times 4 times pi divided by 360 gives me an area of the triangle of 2.6. We'll go ahead and call that 2 square feet. Am I done? Is that my answer? What's the problem with that answer? That's the area of the sector, and I just want this area, that this segment here defines in between the segment and the edge of the circle. So what do I do now? What do you want to do, Sachin? Yeah, I need to find the area of that triangle and then subtract it, right? All right, so let's go ahead and sketch that triangle a little bigger because we've got some math to do. Are you ready? If I draw that triangle, I know I've got 2 feet on this side and 2 feet on this side. How do I know that? Yeah, those are both radii of the circle and sides of the triangle. Hey, I'm going to draw an altitude and I'm going to make it a right angle. That's going to represent the height of my triangle. If this angle here is a 75-degree angle, how do I find these angles here? Anybody feeling some trig coming? Anam, go ahead. So I'm going to do 180 minus 75, and then I'm going to have to divide that by 2, right? So hello, fractions. 52.5 degrees for each of these sides. I need to find my height of this theta. I need to find my opposite and my adjacent, right? So 2 trig calculations. My sine of a 52.5 degree angle is going to be equal my opposite over my hypotenuse. So my opposite is what I'm looking for, and my hypotenuse is 2. So 2 times the sine of 52.5 is going to be the height of my triangle. My door side of my friends, you do that calculation. Window side, listen up. You need to figure out this triangle base. So the cosine of 52.5 degrees is equal to adjacent over hypotenuse. Adjacent is what you're looking for. Hypotenuse is what you have. When you do your cross products, x is going to be equal to 2 times the cosine of 52.5. Don't forget to check your mode. Check the mode, make sure you're in degree, and you figure out the one that you need to do. So when we go to find the area of this triangle, and I'm going to draw a little box so you can see where it is that I'm working, my area is 1/2 times my base times my height. My area is 1/2. My base is these added together. So 1.22 plus 1.22. Anybody think that that's a silly thing to go through doing? What? How come? Because if it's 1/2 times this double, just have it be that 1. So area is equal to 1.22 times 1.59. So the area of my triangle is equal to 1.94. How am I going to find my segment area? Who's still with me? My sector segment was 2.62. My triangle was 1.94. And when I subtract them, I get 0.68 square feet is what my segment area is. Here's why we love geometry. In one problem, we can review Unit 8, area of polygons. We can review Unit 7, right triangle trigonometry, all while teaching you about Unit 9. Do I have that right? Circles. So cool, right? All right, take out your notes from last class, please. All right, everybody join me on the back of notes 9-1A. Take a deep breath and think about these easy ones. The big idea here was to divide your circle up into 360 degrees, taking what you know, 90, 90, 151, that gives you 29. So identifying those angle measures, no big deal. Hey, talk about review. That takes you back to Unit 1. So we can go ahead and talk about the measures of those angles. Now when we talk about the measures of each arc, because they're talking measures, we know we're talking degrees. And I can define each of those arcs. So I know that GJ is the short way around the circle because there's no third point. So I'm not going the long way, I'm doing the short way. HI is just this little one. Now HIJ is a semicircle And I saw another one here where it was 3 letters, but I didn't have to go the long way. Maybe I'm thinking of another one. But you just want to make sure you start at that letter and go the direction they tell you. Any questions on those? You're like, yeah, those are easy. Can the quiz be all of those? You're like, yes, please. All right, find the circumference of a circle with a radius equal 9 inches. Your circumference is equal to 2 pi r. If you're talking about an exact measurement that includes a pi, if it talks about an estimated value, we're going to go ahead and use the pi button. So 3.14 is too general of a relationship. So since you have a calculator, you're going to use it. So I want you to keep using the pi button. Would you turn to your partner, show them where the pi button is on the calculator? Okay. When you go to find the diameter, whether you know your circumference as 2 pi r or pi d, it depends on what situation. An exact value would be 58 divided by pi inches. And when I actually do that calculation, I get that. When we talk about finding the measure and the length of each minor arc, my measure of AB is 70 degrees. My measure of CD is 100 degrees. My measure of EF is 140. And then here are my lengths of my arcs. I'm trying hard to show you both the proportion and the equation so that if you're one of my 2 ways of thinkers, it makes sense to you. Proportion and equation. Proportion and equation. Everybody okay with that? And I love this problem here. Have you ever been on the bike path or around your neighborhood and you've seen like mom and dad on their big bicycle with their big tires? Easy peasy, and the little kid like, like, it's because with the smaller diameter of the wheel, it goes that many more revolutions. So just in 4 inches of difference, a 2-inch difference in the radius, it goes 1 entire extra revolution over just a small distance of 250 feet. So that's an interesting conversation where you take that whole distance and you're dividing it by how many times that circumference rotates around. It makes a big difference. Did I mess that up? 2 pi times 10. No, I did it right. I did the radius. Phew. I was nervous at first. Okay, on the back is the harder one, maybe? I don't know. Do you think the area is harder or the length is harder? Area is harder? First thing you want to do is check and make sure are all your units squared. You're talking about how many little squares fit in that circle. So you want to be talking about square centimeters. You want to be talking about square units, square feet, square whatevers. So the area of that circle, here I had to use my distance formula. Thanks for that review, right? Distance formula to know that my distance is 10. So that my diameter is 10, which means my radius is 5. And they ask for it in terms of pi, but you can also give it to me as an estimated value from your pi button. If they ask you, anytime they ask you for an exact length, then they want you thinking in terms of pi or unsimplified radicals. These are my 2 ways I get irrational numbers. Numbers that don't divide out evenly, no patterns, no ends. So we avoid that if we can. When I go to find this area of the sector, I have this many parts out of this many holes. So this piece of the pie represents 1/10 or 11/36 of the whole. So here's my 11/36 and 49 pi. Pi r squared is the whole. I do my best to break down all my calculations. So when I'm finding the area of the square, thanks for this review, length times width. And then I could have taken the area of the circle and done lots of different subtractions, but I thought it was easier just to subtract this area. 108 plus 108 is 216, so I have 216. I can combine these like that. So out of this 96, I'm going to take away 30.16 and get that difference. For this area of the sector, we made it a lot easier than on your warm-up because it's a quarter of the circle. And that area of the triangle is easy to find because it's a right triangle. So 1/2 base times height. That was easy to find. I didn't have to use any trig for that. Phew. Down here when I had to find that segment area, my math not quite as easy as this, but not as difficult on your warm-up because I was able to use my 30, 60, 90 triangles to get those values. How are we feeling? I'll post this key on Schoology, so if you need to go back and fill in your notes, you can, but for now, would you just set it on top of your baskets? Because I'm going to use the keys for each new class. Sound okay? All right, here's today's conversation. We love circles. There's so much to know, especially when we take one vocabulary word and give it 2 meanings. Right? We're like, thanks for the extra vocabulary. It's like we're double dipping into the academic pool. Hey, we're going to talk about tangent lines. We're going to talk about tangent circles. We're going to talk about the point of tangency. By the time we finish this lesson, you're going to be sick of the word tangent. Okay, so a tangent line, which we're going to say is a noun. A tangent line is a thing. A tangent line is going to be a line that intersects a circle in exactly one point. That point of tangency is where it hits. So that tangent line is a thing that is tangent through the point of tangency. That's that place where it contacts. That point of tangency. When we talk about tangent circles, we can describe the positioning of the circles and how many times they intersect. If the circles are tangent, then they intersect exactly once. So when I look here, I've got 2 tangent circles here and 2 tangent circles here. Each of these circles touches each other exactly once. These tangent circles are internal. These tangent circles are external. So when we talk about the word tangent, it's more of an adjective where it describes the relationships between those circles. Why are these circles not tangent? Yeah. These circles are not tangent to points of intersection. Why are these circles not tangent? Because they don't intersect. You know what we call these circles that have the same center? Anybody know? If they are concentric circles, they have the same circle and it makes you the same center. Makes you want to go shop at Target. A Target symbol are 2 concentric circles, circles that don't intersect. So you can have 1 point of intersection if they're tangent, either internal or external. You can have 2 points of intersections if they cross each other. You can have no points of intersection, and if they share the same center, we call them concentric. Obviously, here we have no points of intersection, and they don't share the same center. But back to tangent lines, would you all please grab a straight edge out of your basket? Because now we get to talk about what these tangent lines are, because we can have internal versus externally tangent lines. If I have tangent lines that touch a circle, that touch two circles, we can say these are external tangent lines. And that externally tangent line hits those circles one time each, and they are outside of the circle. These guys are external tangent lines. If we have internal tangent lines, those are tangent lines that cross an imaginary line connecting the circle's centers. So if I have a line that goes like this, oh, I didn't quite hit it exactly. Hold on. If I have a tangent line that crosses an imaginary line connecting these circle centers, then that is what we call an internal tangent line. God bless you. So for these tangent circles, I can draw an internal tangent line. For these internally tangent circles, I can draw an external tangent line. So I'll go through that one more time. These circles are externally tangent, but this tangent line is internal. Got it? Externally tangent circles, internally tangent line. Internally tangent circles, and what kind of tangent line is this? It's externally tangent. Tangent lines versus tangent circles. Are we good? Here's why we care. Because if a line is tangent to a circle, then it's going to be perpendicular to the radius drawn to the point of tangency. So that means that this angle is guaranteed to be a right angle if this line is tangent. And right away, my brain goes to, how do I prove that? Because in my mind, I want to be like, oh, wait, if I were to draw an isosceles triangle, then I could prove that that radius is the altitude. So through congruent triangles and CPCTC, I can prove that theorem. Now 9-2 is the converse of this guy. So if a line is perpendicular to the radius, then it's tangent. So I get a tangent line if I have a right angle. And I don't know why sometimes we separate our converses versus calling them the converse versus not. I just deliver them as I see them. Sometimes they stand alone. All right, so our last tangent relationship is if two segments from the same exterior point are tangent to a circle. So here's my exterior point. If two segments from an exterior point are tangent, here's my point of tangency. Then this distance from the point of tangency to that exterior point is guaranteed to be the same. And this one's tons of fun to prove because once I have this as a right angle and I have a radius of a circle is always congruent to itself, do you all see congruent triangles in CPCTC? Do you see hypotenuse leg? Here I have hypotenuse, reflects the property of congruence. Legs are congruent, radii, right triangles because of this guy, which means that by CPCTC, those two external tangent lines are always going to be congruent. All right, go to lunch and think of tangents. And in this section, we're talking about chords and arcs. And the most important phrase that we're going to get all the time is within one circle or in congruent circles. And the reason why we need to say that over and over again is not because of our angles or our arcs, but because of our chords. So when we're talking about that circle, we need to make sure that we're talking about circles of the same size. Are we talking about a circle this big? Are we talking about a circle this big? Or does it not matter? If we're talking about angles and arc measures in terms of degrees, the size of the circle does not matter. So whether you have an itsy bitsy circle or you have a huge circle, it doesn't matter. This is going to be X degrees and this is going to be X degrees. If you're told that these two angles are congruent, these two arcs are congruent, that's a no-brainer, regardless of how big of our circle is. Within a circle are congruent circles, congruent center angles have congruent arcs, no problem. Backwards, within a circle or congruent circles, congruent arcs have congruent angles. So my arcs and my angles, not a problem. It's when we get to talking about these guys that life becomes a different story, because take your straight edge and draw the chord. And the chord that we're drawing is the one that's defined by those radii that create the arcs dictated from the angles. And this is what we care about, and this is why this phraseology within one circle or congruent circles, that's why that matters so much. And again, I don't know why. Sometimes the converse is tucked in, and sometimes it's its own freestanding theorem. It's a mystery to me too. But basically, you've got these three conversations: angles, arcs, and chords. If the angles are congruent, the arcs are congruent. If the arcs are congruent, the chords are congruent. If the chords are congruent, the angles are congruent. And you don't have to remember specific which is the converse or which is what. Anytime that one of them is congruent to another part, they're all congruent. So we want to make sure that we're talking about our central angles can be congruent And I'll go ahead and I'll change this color for our related arcs are congruent to our chords. Once you have that scenario that's true, it's true for all of them. And again, none of this is particularly difficult. It's just a lot at one time. That's why we have to make sure we use our notes, because when you go back and look at your notes, you're like, oh, all right, I get that. I remember that. Not a problem. That's that one about arcs, chords, and angles. All right, so we can come down to these practice ones. And here's what I can conclude. What kind of angles are these? What's true about vertical angles? Once I know that these angles are congruent, then I can go to town. Because once the angles are congruent, I know the arcs are congruent, and I can mark that with a little mark. And once I know the arcs are congruent, I know the chords are congruent. So just from one idea of vertical angles, I now have my arcs and my angles and my chords. And that's just true within this circle. Once somebody tells me that these two circles are congruent, then I know, and these two chords are congruent, then I can go backwards. I know that I have angles and arcs galore. So whether you're working within one specific circle or talking across circles, that's what we mean by within this circle, vertical angles is going to prove all this. Or in congruent circles, once I'm told they're congruent, these congruent chords are going to guarantee congruent arcs, are going to guarantee congruent angles. Sound okay? All right. So in our next big idea, we have that same phraseology in the same circle or in congruent circles. Two minor arcs are congruent if their corresponding chords are congruent. So once I have this distance that is the same as this distance, then I know right away these two arcs are going to be congruent. Two minor arcs are congruent if their corresponding chords are congruent. If the arcs are congruent, then I can go ahead and say that my angles are congruent also. Okay. Moving on. More conversations about arcs. And that is this. In the same circle or in congruent circles, there's that phraseology again. Two chords are congruent if and only if they are equidistant from the center. So by equidistant, we're talking about this distance is the same. And remember, we measure distance with what kind of angle? Always a right angle. So if those two chords are equidistant from the center, I can guarantee that those two chords are congruent if they're equidistant from the center. Because those two chords are the same distance from the center, I can guarantee that these chords are going to be the same. Anybody know how we prove this one? I'm saying that if EG and EF are congruent, A, B, and C, D are congruent. Anybody have an idea of how we could prove it? What do you think? Yeah, so it looks like these are both bisected, right? But we don't know that for sure, but you're so close. What kind of angle is this? 90. So if we were looking for congruent triangles, is there anything that we could maybe do? You're right, they're bisected, but we don't know it until we get the congruent triangles. How do we get the congruent triangles? You're like, what triangles? I don't see any triangle. Anybody see a triangle? Do you see it? Go ahead. Do you see these triangles?
Yeah, I saw the second one.
What are these purple lines? What are they? Say it out loud. What are those lines? Yeah, they are radii, first of all. Second of all, they're the hypotenuse. So do you know that all the purple lines are congruent? How come? Because the center is the center of a circle, and it's the same distance to the radii, and the radius. So all the radii in a circle are congruent, so every single one of those purple lines is congruent. Keep going, keep thinking. Come on. Somebody said that they thought the purple lines were a hypotenuse. Were they right? Yeah. Yeah, they were right. Because it's the longest side of the triangle opposite the right angle. So I've got all my hypotenuses, hypoteni. I've got every single one congruent. Radii, hypoteni, opposite. And what was I given? What did they give me was congruent? Does that look like a hypotenuse leg? Yeah? Look how we keep reviewing. It's like the SOL is coming up or something. Leg, hypotenuse, right angle, 4 congruent triangles. So by CPCTC, Sebastian wanted these to all be congruent. Is he right? Yeah? Because by CPCTC, corresponding parts of congruent triangles are congruent. All of those little orange lines are congruent. Therefore, segment addition postulate, when I add them together, what? Now, it's a theorem. Somebody went to the difficulty of proving it for you. You don't have to prove it, but you could. Because by CPCTC, all those little orange segments are congruent. I can use CPCTC because my triangles are congruent. My triangles are congruent because the hypotenuse leg. I have the leg that was given to me, and all the hypoteni are radii of the circle, the same circle. Two chords are congruent if and only if they're equidistant from the center. So when we look at these problems real quick, if this is 3, and this is 3, and this guy's 8, this guy's 8, this guy is not a problem. You okay with that? these are all congruent, and we're going to go with this whole leg, this whole segment's 12, because it's kind of positioned in the center, and this whole segment's 12. So if this guy's 5, what's x? It's also going to be 5. And these markings become so important. If this is 4.9, so is this. These two chords are equidistant. So if this is 6.3, so is this. So that makes x is equal to 12.6. You okay with that? All right, here's our last new idea for today. Are your brains full? It's okay, it's good for you. We're going to talk about 3 different things. And the rule of thumb is anytime you have 2 of them true, you have the third. And we're going to talk about diameters, which is a chord that goes through the center of the circle. We're going to talk about perpendicular lines, which means they intersect at 90 degrees. And we're going to talk about bisectors, which means it's cut equally into 2 pieces. When you look at each of these circles, you have 2 of those 3 things. Do you see the diameter? Do you see the right angle? Then you know that this segment is bisected. That's your therefore. Come down to this one. Do you see the bisected? Do you see the 90 degrees? So now you know that this is a diameter that goes through the center of the circle. What do the 3 dots mean again? Do me a favor and draw which one I'm missing. Draw a circle for yourself. My circle's not that great. Here I have the diameter that's a right angle, therefore bisected. Here I have the bisected at a right angle. So what am I missing? Which one am I missing? If I have a diameter that bisects a chord, what do I know is true? It's going to be perpendicular. So our theorems go like this. If the diameter of a circle is perpendicular to a chord, then it bisects. The chord and the arc. So DE is congruent to EF, and arc DG is congruent to arc GF. If a diameter bisects a chord that is not a diameter, that's perpendicular to the chord. If one chord is perpendicular, bisector of another chord, then the first chord is a diameter. Anytime you have 2 of those conditions, you have the third. So for me, this is what I remember. Two out of the three gives you the third. All right, so here's a pretty cool application of that. And this is a true story of how this works in real life. An avalanche rescue beacon is a small device carried by backcountry skiers. It gives off a signal that can be picked up only within a circle of a certain radius. If you buy a pair of ski pants in today's world and you buy them from an actual ski place, like not Costco or Kohl's, the ski pants come with a little magnetic strip in them. So my ski pants in the one liner has a device that sends a signal if I were to be buried under the snow. So what's really cool is I want you to imagine me buried somewhere in the snow. And these theorems is how they actually go ahead and they use the geometry to find me. And it goes like this. When they're looking for me, they come walking along. And they come walking along. And this is the first time that they can see my signal. I'm buried here. And this circle is the radius of the signal that my little thing sends. Out it goes. And when this guy's walking along, he has no idea at what point of entry he hits my circle. He could hit it here, or here, or here, or here. So he marks this point A. And then he continues walking in a straight line, listening to my signal until my signal stops. And he marks that point B. That's where he doesn't hear my signal anymore. Does that make sense to you, him walking outside of the radius? All right. Then he turns around, and when he turns around, he counts back, and he finds the exact middle of that distance, and he marks this point C. At this point, he guarantees that he walks at a 90-degree angle, and he walks this way until he doesn't hear the signal anymore, and then he walks this way until he doesn't hear the signal anymore. With your group mates, explain how he finds me. Turn and talk. How does he find me?